Hello students, so in this lecture we will start discussing about some fundamentals of some electronic devices. We will first start our discussion with something called a P-channel Mosfet. Now, P-channel MOSFET is a metal oxide semiconductor field effect transistor. So this MOS stands for metal oxide, and this FET, on the other hand, it stands for field effect transistor. Now, when we talk about MOSFET, we mainly mean SiO2, but we will have also started using titanium dioxide in place of SiO2, and it is preferred over SiO2 because the relative permittivity of TiO2 is less than SiO2, and so it permits the tunneling of K layers across the thin oxide layer. So it permits the tunneling of carriers across the oxide layers. Now, a MOSFET has got three so when you talk about a P-channel MOSFET, it consists of a P-channel source or P-type source, and a P-type drain, and N-type bulk. Now, if if there is an N-type MOSFET, so basically it looks something like this. So for the P-type MOSFET, you have a bulk N-type, and you have basically two P-types, and you have an oxide layer. Sorry, this is how an P-type channel looks like. It will be opposite if we have an N-type MOSFET. For example, this N and this P will be replaced by, this will be then N, this will be then P, this will be N, and this will be N. So when this is an N-type MOSFET. So when we have an N-type MOSFET, the number of donors is the concentration. If N is the number of electrons, is the number of donors, and if in the depletion region, the number of donors is much greater than the number of electrons, and it is also much greater than the number of holes. And in the inversion region, on the other hand, it's the opposite. The number of holes become less than the number of electrons. So if we have an N-type MOSFET, made up of silicon, and say the number of donors is 7 into 10 to the power 6 per centimeter cube, and then intrinsic carrier concentration is 10 to the power 10 per centimeter cube, and it is at room temperature 300 Kelvin, and the voltage required to make surface intrinsic. So I ask you to find out the voltage required to make the surface intrinsic. So for that we need to find out the electron concentration at the surface, and that electron concentration is given as Ns is equal to Ni e to the power minus phi s by phi b by kt, where phi s is the surface potential and phi b is the bulk potential. Now, since we would like to make the surface intrinsic, for the surface to be intrinsic, Ni should be equal to Ns. So that is the case, and if we see Ni e to the power phi s minus phi b by kt, so that makes e to the power phi s minus phi b by kt is equal to 1. So that means phi s minus phi b by kt should be equal to 0. That means phi s should be equal to phi b. This is the condition for making the surface intrinsic. Now phi b, the bulk potential, is again given as the contribuable due to n-type doping in the bulk minus the intrinsic formula in the bulk, and it is nothing but equal to kt ln nd by ni. So we started with the concentration. Started with nd is equal to 7 into 10 to the power 16 per centimeter cube, the donor concentration, and intrinsic carrier concentration was 10 to the power 10 per centimeter cube. So the surface potential phi b is kt, where t is at T is 100, so it corresponds to 0.0259 electron volts. So it's KT ln ND 70 to 10 to the power 16 divided by 10 to the power 10. So that if you put the values here, it turns out to be 0.41 electron volt. This is the bulk potential, and this has to be equal to the surface potential to make the surface intrinsic. So you can see that this is the voltage, and so 0.41 volts is the voltage required to make the surface intrinsic. Now, if somebody tells you, see, for the same concentration, what is the voltage required to create a strong inversion? Create a strong inversion at the surface. So a strong inversion is the surface is as much p-type as the bulk is n-type. So by strong inversion, it means the surface is as much p-type as the bulk is n-type. So remember, we are dealing with an n-type MOSFET here. So you have got an n here, and there is a p and there is a p. Sorry. So, right. So there is an n, there is an n, there is a p. So for this to happen, the bulk, the surface potential should be twice of the bulk potential. For just inversion to take place, the surface potential has to be equal to the bulk potential, but for a strong inversion, the surface potential will be twice of the bulk potential. So it will be simply 2 kT ln nd by ni. So it will be 2 into the previously obtained value, 0.41 electron volts, that is 0.82 electron volts. So the voltage required for strong inversion is 0.82 volts. Now, a junction, a PN junction, JPN, the PN junction, it is basically a P-type and an N-type coming in together. So it has got two terminals. This is the one terminal and this is the one junction. So it's a two terminal and one junction device. But if you talk of a transistor, for example NPN or PNP, whatever, let's take an NPN terminal. So there are three terminals, 1, 2 and 3, and there are two junctions. So a transistor is a 3-terminal two-junction device. Now there are two different types of transistors. One of them is called a BJT transistor. It's called a bipolar junction transistor. So there is an emitter, there is a base, and there is a collector. So we have two junctions. One is the emitter base junction, another one is the collector base junction. So we have emitter, base, and collector. So this is the emitter base junction, and this is the collector base junction. And in this case, the depletion region is almost entirely in the base. And the junction between the collector and base, this is divided equally. The depletion region is divided equally. The reason is that, so when we are talking about an electron emitter base junction, the depletion region is entirely in the base, whereas when we are talking about a collector base junction, the depletion region is divided equally between the base and the collector. This is mainly due to the fact that the emitter is heavily doped. The emitter junction is heavily doped. So sometimes if we are using an NPN transistor, so we usually call N plus PN transistor. When this plus indicates that it is heavily doped, whereas the collector region is comparably doped. And NPN junction, JFT stands for the junction field effect transistor. The junction field effect transistor, for example, if we are talking about an NPN junction field effect transistor, and there is an N channel existing in the absence of gate voltage. Exists in the absence of gate voltage. So instead of an emitter base and collector, as in the case of a novel transistor, in a junction field effect transistor we have source, gate, and drain. So the N channel will exist only when there is a gate voltage. Even if there is no gate voltage, and it is a voltage controlled device. So JFET is a voltage controlled device, and the current flows depends on the width of the channel, which is controlled by the external potential. So it implies that the current flow depends on the width of the channel, which is controlled by external potential. And when we talk about an N channel junction field effect transistor, the gate is shorted with respect to the source. So that makes the VGS is equal to 0, and the drain is positively biased with respect to the source. So that makes VDS is greater than 0. And we can even find that the N channel near the drain starts narrowing with an increase in VDS. So when we increase the drain source voltage, so you have a source, you have a drain, sorry, the source, we have a drain, and we have a gate. So when the source the drain source voltage, this is put as equal to 0, it is shorted. When the drain source voltage it increases, when this increases, the drain starts narrowing with an increase in VDS. The N channel near the drain, near this one, starts narrowing. So it implies that this is mainly because of the fact that the drain gate junction is reverse biased. This is reverse biased junction between the drain and gate. This is reverse biased. Therefore the N channel starts narrowing down at the drain.